Okay. Welcome everyone. We are a small and independent group of researchers who organize talks and panels and podcasts, primarily targeting computers, system students. And if you like this discussion, please follow us on Twitter and LinkedIn. My name is Tanvi Sharma, and I'm a fourth year PhD student at Purdue University. And my co-host today is Huying Lee, who is a PhD student at Cornell and a visiting PhD at MIT. Today's podcast is focused on machine learning systems, or MLSys. And we are thrilled to announce our two esteemed guests today, Professor Gennady and Professor Cheng. Professor Gennady is a faculty at University of Toronto and is also affiliated with Vector Institute for AI. He is also associated with another company which he started with his students, Spent ML, which offers optimization platforms for ML training and inference. Prior to his current role, he has held positions at Amazon, Microsoft, NVIDIA, IBM, Intel Labs, and has won significant paper awards in the field, including grants and fellowships for his work in memory systems and systems for machine learning. Professor Cheng is with Northeastern University, and his group focuses on building systems that enable users to verify their outsourced services, with recent focus on verifying neural networks for systems. Before joining Northeastern, he also worked with ByteDance AI Lab and has received several awards, including the NSF Career Award. Welcome all. So I guess without further ado, let's dive in and initiate the discussion. So we can start with your career experiences. Both of you have had a journey through various educational institutes around the world, with Professor Gennady going from Russia to Canada in University of Toronto, and then back again in US to CMU. So it has been geographically different for both of you. And also Professor Cheng here started his journey from China, then to New York University, and now a part of Northeastern. So could you share about your journey through these institutes, how these environments, especially the working culture, research exposure, and funding opportunities shaped your career path?
Yeah, I'm happy to start. So I guess I had quite a diverse experience, and I had to say that things are quite different, especially between Russian ecosystem and what you had in Canada and US. But all of that experience was very helpful. I guess the first time I learned about the whole grant system and how, resources are given when I actually moved to North America. And the academic environment between Canada and US is not dramatically different, but there are differences, right? So in US, when doing my PhD, I learned about the, NSF and DARPA and other programs that are quite massive, but also very competitive. In Canada, the emphasis is more on collaborative efforts. There are a substantial number of grants, but they're usually collaborative across different areas. So there are differences. Also, in general, the model of distributing funding is different in Canada and US. So those nuances that do affect things. My own experience is that I really appreciate working with industry a lot. So I've spent more than 8 years of my life working with industry. So a lot of my academic research and also, the work I do in funding are coming from industry collaborators. So that was true in Canada. This was true in US. I think it's going to be continued moving forward. Yeah. So in terms of educational system, I guess there are pros and cons in each system, right? Overall, I think certain schools do more emphasis on research and some other schools more on educational and undergrad. Like say in Russia, there was a very good undergrad system. but moving to grad program was not as easy or as smooth, and research was not as big of an emphasis. While in US, obviously, a lot of things are focusing about how quickly you jump in research. I have students right now starting to do research in their second, even first year, right? Something that's it used to be unusual when I was an undergrad student myself. So this is the changes I see, and things that I guess that's where the direction is going. Like students get engaged in research really these days. Yeah.
Yeah, that's a very good point. Even I have observed that compared to India.
Yeah.
Yeah.
So I totally agree. So I think industry experience is definitely very important because as a computer, let's say scientist, right? You need to solve the right problem, where a lot of our right problems come from industry. That's where the true challenges happens. In terms of my experience, I did my undergrad and also master's in China, and also I got my PhD from NYU. So I do like feel the two systems, one in China and here in US, they're very different. So my thinking of sort of the core skills of having a good career, for example, in research or in academia, is you need to have a really good research taste, and also you need good execution skills and also the communication. So I think in terms of execution, right, the coding or the technical skills, I learned a lot from my undergrad and also masters, where I hacking kernels and stuff like that. Where the most appreciated skills I learned from NYU is that I gain a pretty good research taste from my advisor, and communication skills as well. I think that's how I feel the focus of for my personal experience, right? So I learned different skills from different stages. But yeah, in general, I think for the audience, right? So if you want to be plan for your career, you should at different stages you should think about, so for my current focus, should I focus more on polish my implementation skills, versus sometimes you should really looking for research wise taste, or communication wise, you should, for example, how to become a good speaker and giving presentations and stuff like that. But yeah, that's my thoughts.
Yeah, that's an interesting point. So if I were to summarize both of you, it's best to learn the skills and implementation details when you are in undergrad, so that you can ramp up faster in research during your graduate school. And I guess US and Canada offers more research experience even for the undergraduates. So moving forward, Professor Gennady, since you decided to come to Canada, before that, during your PhD, you have had an interesting career transition, working on memory compression and DRAM to now MLSys. So what sparked that change? And another question is, one of your advisors, Onur Mutlu, he heavily advocates for data-centric computing. What are your thoughts on that?
Yeah, so several things here. So why MLSys is an area? There are several moving factors. First of all, I did my master's at U of T, as you mentioned yourself. You've seen it in my career path. So while doing my master's at U of T, while being a systems student working on compilers back then, I took courses in ML at University of Toronto, and one of that courses was with Jeff Hinton. So obviously, it was a very profound effect on what's possible. Like I learned about that, and there were like a lot of other amazing people in ML space. So after that, I used ML in my master thesis when it was not popular. We're talking about 2008, right? I use, not deep learning, but traditional, logistic regression and MLPs, right? And then I had that in mind towards my PhD, but ML was in its long winter during then. And then, AlexNet happened, ResNet happened, a lot of progress and computer vision model happened. So by the time I was graduating in 2015-16, it was clearly on the right track. So there were two things. So first of all, in 2016, when I graduated and got an offer from UFT and other schools, I decided to pause that for a year, to join in a year and join Microsoft Research. So when I joined there, I spent a year looking at what the real problems exist in industry. And ML training was a huge problem back then already in 2016. There was a shortage of GPUs already, lines of people, and clear no right metrics. So there were tons of problems I can work on, which was a good opportunity. And another reason is, as you establish yourself as a new researcher coming off PhD, you don't want to be treated that's the only thing you can do is what you did during your PhD. So I picked several new directions that were completely different with from my PhD, right? So something I like, that's, that would be, I'm never afraid of changing directions, right? So it's not like I stopped working on memory system, it's just, I pick a few other directions and they start to pick up so much faster, right? So the guess was correct. So originally I was planning that I'm going to spend about half time on ML and systems problem and half on computer architecture. Right now it's more like 70 to 30 in favor of ML systems.
Yeah.
Yeah,
that's a really interesting point of view.
In terms of data-centric computing in general, I do think it's true and it's the right way of thinking. Even the way when we talk right now about LLMs, for example, I think the same way. I think that actually the technology of models itself becomes commoditized. So the people who have the data would have the advantage, right? So they would train where the data is, and then they can benefit from that data and generate IP out of it. That has many different implications. You can think about data-centric computing with respect to computer architecture, but I think it's a more general principle. The data is the new gold, and you're going to monetize it in different flavors, right? The last year, people felt that building LLMs is the secret sauce. It still somewhat is, but I think it's getting more and more commoditized. Right now, there are a lot of really easy to use open source models that are not that far, let's put it this way, from even GPT models, right? So it means that people can just take them and already get benefit, right? So I think it's a good view in general moving forward beyond even computer architecture.
Nice. Yeah, that was also interesting to know that Hinton played a role in you going to MLSys.
Yeah, that's great. Thank you for sharing. It's quite inspiring to see how this data-centric computing philosophy is now being more popular in the computer architecture community and in the MLSys community in general. So maybe moving a little bit forward, I also had a question for Professor Cheng. So you had many interesting works spanning from verification to systems. And recently you had some really interesting work about DNN serving and verification of DNNs in MLSys. So this is a very unique and new angle. I was wondering, how do you choose these problems? And are there some conscious decisions you made with respect to choosing this type of problems to work on?
Okay, so I see I see myself as a systems person. So my home community is in operating system, right? So actually all my work is to build better systems, but by better, it can be faster in terms of performance or more secure, or, with more formal guarantees of correctness, for example, right? So that's why, even if you see the, titles of my papers can span from verification to systems to outsource, computing or whatever. But the core is there's always a focus on systems itself. So in terms of today's topic, MLSys, right? I do see there's a huge opportunity here where we can use or leverage machine learning, or in particular deep learning, right? To have build better. Again, better means many things. Better systems. And in particular, I think one of my focus right now is combining this verification with neural network for computer systems, which we call verified MLSys. So the opportunity here is that we do find some opportunity that we can either finding better heuristics, right? Meaning faster systems, or reduce some of the human efforts of building systems optimizations, where we can just use machine to optimize for that, or we can have more secure in terms of verification for methods secure system that we can work on. So yeah, so I hope that this direction is the starting point. I hope in the future we can make more progress on this line of work, which can sort of refurbish how people build systems or build better systems. Yeah.
Yeah, that's great. Thanks very much for sharing your vision as well. I think making the neural network as secure and as robust as possible would be a very important agenda to leverage more power in the system community of the neural network. So maybe now let's dive a little bit deeper into the machine learning and system domain. One part of developing systems for machine learning is developing the infrastructures and also the simulation frameworks to help bring ideas through to reality. And I think there are a lot of infrastructures that are amazingly done by Professor Gennady's group. For example, his recent project on HEDAT, which is a specialized compiler for deep learning, and also he has some performance profiling and prediction infrastructure called DeepView, which is also very cool and introduced in SPLOS workshop this year. So building infrastructure to serve the MLSys community, I think is a very important agenda. And I was wondering, Professor Gennady, how do you see them growing in the future, and what are the most challenging part when you are building these projects?
Yeah, so thanks a lot for bringing this topic in. I will start with the DeepView. So the DeepView is the project that encapsulates like more than 4 years, if not 5 years, of our academic research first, multiple papers there. So the grand vision here was like that. So people who build models are people with ML skills. Very frequently what they learned and supposed to know, they know Python, they're familiar with PyTorch or JAX, but they're not familiar with GPUs or TPUs or CUDA and these low-level things. So nevertheless, they're the one that face the problem when the models doesn't perform well, and they were not given the right tools to do their job properly. What does that mean? The first problem, they don't understand what's good or bad for them and which hardware they really need. They were just listening different, use or marketing materials from different companies, but they don't really know what the best for them and for their specific model. The second problem they need to handle is that they build the models and frequently get things like out-of-memory violation, but they don't know where that memory comes from. The only thing that NVIDIA SMI would tell them as a tool is how much memory they consume, but where that memory goes. There were no good tools at all to do it. And we learned that by working at Microsoft Research and working with Vector Institute, that this bothers them because they get out of memory. What should I do? Should I cut the number of layers? Should I reduce my batch size? Should I reduce the number of parameters? They usually do random things, and it didn't help because they don't know where the real bottleneck is. So coming from a systems camp, but that's a norm to have these tools, helped me to build them and be the first one to do it and make visibility out of them. Right now, there's so much interest that we even asked to present at Google and Matter, like in the coming weeks, to show the DeepView and how it's used, because they don't have anything like that themselves, right? And they already see the value of that. So that one aspect of DeepView, to understand what happens with your model. The second important direction, both like compute and memory. The second aspect important is people want to know what the best hardware to use. The problem right now, if you want to know how well you're going to run an H100 or A100, when your desktop is something like 20i TTI, for example, you have to go and buy it or rent it, right? It means you need to move your experiment into the cloud, do all the evaluation to see it. So we built something that allows you to make the prediction and estimate your speed without doing any of that quite accurately. It's possible because ML workloads are very regular. So you can just use one GPU on your desktop to estimate, to do profiling of your model, and then I can do a very accurate estimate on a different GPU, knowing what the difference is. So that's something we built that allows the people to find what the best hardware would be for them without buying it or renting it, right? So it's like a very quick free estimate. And the DPU is open source, and anyone can play with it, right? So we're going to put a lot of effort in promoting it in the community moving forward. Then having all of that, after that, you want to run your things efficiently. This is where different technology can come into place to optimize workloads. There are two major directions in that space. So you can either use machine learning libraries or machine learning compilers. Machine learning libraries, this is the things like cuDNN or cuBLAS or cuTLAS. This is something that the vendors provide. They're good if your layer or your model is exactly the way they expected it to be. But if you start to do some changes, that might be not the best way to do it. It might be not tuned the right way for you. Then the goal here is to be more flexible and being able to provide models quicker to the market. So this is why we built HiDAT that allows you to get very quickly optimized kernel with no experience needed on CUDA. You can write everything in Python, right? Even system developers don't like to write a lot of CUDA code. It's very difficult in general. So this is why HiDAT is good. So it allows you to get very high performance, sometimes even better than NVIDIA TensorT, for example, while having very minimal engineering time. And the net effect of that, for example, like 2 weeks ago, there was Llama 2 announced, right? And we had optimized inference more than twice faster in just 2 days. And that was done by an undergrad intern. Why is it possible? It's because we're avoiding writing a lot of low-level code. We made sure that all the low-level code is synthesized using our compiler. So we synthesized CUDA instead of writing it manually. So it allows to port all these gazillions of popular models very quickly, right? And get top performance, right?
Okay.
So those are like our contributions, both from the academic perspective and from the business perspective. Right? Okay. HiDAT, by the way, is also open source. This is an inference compiler. Yeah.
Yeah, I think all these works are pretty relevant and also useful for the industry as well, not just academia. And
yeah, so for example, HiDAT we integrated with PyTorch 2.0. If you want to use it, you just need one line of code in your PyTorch. You just write pytorch.compile your model name and the name of the backend, HiDAT, and it's invoked, right? And it's faster on majority of the model than any other alternatives available right now in PyTorch. But the good thing about it, like what I learned about ML people, if you want to give them a solution, it better be a one-line solution, right? So they don't want to learn too much. So make sure they use their most preferable tool, PyTorch, right, or JAX. So this is why DPU is integrated with PyTorch. This is why HiDAT is integrated with PyTorch. This is PyTorch or community, and Meta is our big, collaborator on all this project, because that's the ecosystem people like. We try to integrate all of that so it's convenient for people.
Yeah, I think ease of use is a very good point. I mean, if you're building something, it should be easy to use.
Yeah. One thing we learned is that essentially it's very hard to make one interface that's good for both system people and ML people. So this is why what we try to do in HiDAT, we try to make it that for ML people, it's just one line integration. It's very easy for them to use if they like it. For systems people, we provide them the ability to write efficient kernels, but we reduce the burden on them. So we just make it possible for them to write most of the kernel code in Python, and all the CUDA code is generated from what they want. And all the auto-tuning labor work is fully automatic. You don't need to sit down and do hyperparameter tuning of that kernel, first on 800, then on B100, then on T4. This is all done automatically by the compiler.
Nice. Yeah, that's a very good point. Yeah, since we are talking about the infrastructures, Professor Cheng, you also had a recent work on MLSys, which is a random DNN generator and fuzzing infrastructure. Could you share your thoughts about it and MLSys on the verification of neural networks?
Sure. I think this is okay. So MLSys is a fuzzing tool for deep learning compiler. So we definitely should fuzz HiDAT at some point. It's a pretty cool piece of work because interestingly, the very original goal of this project is not building a testing tool. our original plan was building a verification tool. So we want to verify, the equivalence of the network before and after compilation. So, but like later we find that there's a lot of bugs, so it became a bug testing. But that's a kind of the backstory of this and Smith's tools, and yeah. So I think in general, compiler is like a major infrastructure for today's ML deep learning, infrastructure and systems, right? And we better make sure that so what compiled before and after should be equivalent. Yeah, so that's the very motivation of this Smith's work. And also the verification. Yeah, that's a very different line of work I'm doing. As I mentioned, right? I think so. Like deep learning compiler or MLSys, these are basically systems for machine learning, right? Where the verification, that line of work is about how we can provide machine learning for systems with guarantees. So that's where these are sort of two different directions of my research. Yeah.
So what kind of guarantees are we talking about here? I mean, what is robustness for neural networks? Many people, don't know about this. So could you talk about that?
Sure. That's a very good and very hard to answer question, because it depends on what MLSys we're talking about, right? So I'll just give one example, but it can be many different safety rules or people want. For example, let's say people do use neural networks to replace scheduler, right? Basically, people want to use neural network to make scheduling decision, right? For example, now for this particular application, so the safety rule can be something like, oh, you should always return a valid job ID, for example. So the scheduling decision should be valid. For example, you should never schedule a non-existing job, for example, right? And this is not super interesting. The interesting ones are, for example, I don't want starvation, right? How can you make sure that the output of a neural network-based scheduler, there's no starvation, right? Something like that. And for different applications, there's going to be different like safety rules, right? So the scheduler is actually a pretty hard one. We haven't conquered that. That is the working on progress, and there's a lot of challenges. But the ones we did achieve, for example, is learn index, where people use neural network to replace index, where input is just a key, the output is the position. For such a application, the safety properties can be that you use neural network to replace this index, but you need to guarantee the output is error bounded, right? You cannot predict some arbitrary output, so the output should be within a certain bounded error. So this is, for example, another safety rules for this learn index specification or safety guarantees.
Yeah, I hope you come up with the scheduler part soon. Now, since we are talking about MLSys, we cannot leave this topic without mentioning MLPerf. And we have Gennady here, who have been a part of this initiative since it started. So how did you get involved in this effort to standardize ML benchmarks, which was the first of its kind for inference and training? And could you reflect on this journey?
Yeah, it's a whole topic on its own, can take the whole hour. I try to be brief here. So essentially, already remember when I told about me going to MSR, Microsoft Research, one thing I noticed in 2016, there was no standard way to compare things. Back in 2016, anyone can claim 100x better than being others, and there was no way to validate it. And it was, when you start to take the code, you see this is not true, but it was wasting everyone's time. So in systems, it's a known problem, like we had spec benchmark suite for ages, right? And that's allowed to, collect it. But in ML space, I quickly realized people are working on a particular model and they don't do systematic benchmarking, which is okay for ML research, but it's not okay for people who build systems. So this is why in 2016, I decided that I'm going to work on ML benchmarking. And I started to hire my first students in University of Toronto before joining. That was their first project. Like pretty much every single student of mine in their first project in the first year was helping with ML benchmarking. We called it TBD suite, and it was partially TBD because it was always to be done. Like by the time you finish the benchmark, there's a new model and new benchmark is out there. So we made that publicly available in 2017. And then I got contacted by two people independently. First, I got contacted by Google, by Cliff Young, and I also got contacted from Stanford by Matej Zaharia. And they told me that they are interested in building benchmarks. So it doesn't have a name, they didn't have a project, they just exchanged some emails, right, internally. And they joked, it's like, do you want to build your own thing separately, right, or you want to join the effort? I think Matej and Peter Baylis had something called Dawn Bench as well that also looked at benchmarking, but from a different angle, from ML side. They look at accuracy, while my benchmark look at speed, like from systems perspective. And this is how we started it. There was no name MLPerf in our first meeting. There was around 10, 15 of us that gathered on campus at Stanford, and the first few meetings, that was pre-COVID times, so people were not doing meetings on Zoom as frequently, or Zoom was not popular. People were using still Skype or Google Meet. So I had to flew very frequently to the Bay Area for those meetings, right? Sometimes the same day back and forth to Toronto. And that's how it starts to shape, and that's how we build MLPerf. And then there's a lot of, at the beginning, it was hub-driven by academics, right? But as you can imagine, as soon as people see the value, it was quickly overtaken by industry, right? So we built a few first benchmarks, like we built speech benchmark based on deep speech, based on not deep speech. There was one of the speech recognition model out of Baidu that we used as well. A lot of other benchmarks that we pushed on, and we built initial methodologies. We came up with that was all described in the papers, right? Very interesting experience. We grew it from like 10, 15 people to like more than 1,000 people involved right now. So it's now has actually, it was all, volunteer work before. Now it has a ML Commons organization that had licensees and people, industry actually paying for participation, things like that. It's a very big org right now. But yeah, it was nice to see how things are shaped out. And then I'm still part-time involved in ML Commons and MLPerf research group, like together with Jay already. And again, it was a really great experience for me personally. So I work with like Dave Patterson there. I work with people from Stanford, people from NVIDIA, Google, Microsoft, like all companies you can name. Like all they send representatives, to work on MLPerf and ML Commons. So yeah, so right now, again, it's overtaken by a proper org that oversees. That's how it should be. But academia played a critical role in this happening. So like the initial, I would say more than half of contributors were actually from academia, right? Yeah.
Yeah, it's always good to see academia works getting involved with industry, and ML Commons is definitely a really good initiative, helping the whole academia and industry. Yeah. Also in reviewing papers, it comes handy.
Yes. And yeah, so it's essentially, you can see, especially for students when they think about how you select topics, well, you pick something that industry might not even think is needed, but if you pick it right, they would jump on you, right? Like, and we'll join like that. It's, as I said, there were Google there, Baidu there, and a few other companies, but at the beginning it was mostly driven, at least half by academics, right? So you need the vision, you need to see where the problem is. And then people will join, right? Like very few companies see the necessity. And then a lot of people join, like, look what Meta did, Facebook and then Meta, right? They realize that, say, the current benchmarking in MLPerf, when we build it first, doesn't have recommendation models. And they said, why you don't guys do research and recommendation models? And said, like, well, it's just because you and Amazon has the models internally, but no one has them. Like, you can't do research and models we don't see. So they thought about it and spent money and effort internally at Meta and Facebook to build the benchmark. This is how DLRM came up. And then there was a lot of publications, not just from Meta, but from academia right now, because there is something to optimize, right? There is something to improve. There is a reference point. Before, who would know what exactly recommendation model look like? How can we help, right? So that make them realize that, oh, CNNs are publicly available. Then transformer models came up, they become publicly available. Obviously, people start to use it, but recommendation model were not. So you don't get things, done if not the case. And right now there are a lot of publications on, recommendation models, right? This is how the industry learned from our experience and, do things for their own benefit and they invest things, right? Yeah.
So a quick question, will the next one be on language models then?
Yeah. So what's the question on language models?
Since the MLPerf right now contains image and classification and recommendation models, I'm guessing the next series will have language models, some standard for them.
There are going to be something like that. Remember, there's already transformer models were from the very beginning, right? And then we get BERT model. So the problem with LLMs is, especially for training, they're humongous. So you want that benchmark being accessible. So in a way, from a systems perspective, you just need to make sure that your building blocks are representative enough. So I don't necessarily need to train GPT-4 to prove that my chip is good. What I need to make sure, I train a smaller version of the model, right? Scaled reasonably and show that throughput is reasonable. From a systems perspective, is good enough. ML people need to validate that the model we pick is representative, right? But other than that, we don't need to necessarily everything run at that large scale. Mostly because it's just enormously expensive. Like, how many people in the world can afford training those models, right? So that's the challenge. BERT pre-training already expensive for many academics to do.
Right.
So yeah. So I think it's probably going to be more involved, but even for inference, like if you think about the scale of these LLM models that I have to optimize right now at CenterML, like inference take the whole DGX box, like not training, inference, like the model is so large, you need to do model and pipeline parallelism across GPUs, right? Because it doesn't fit even A100 or H100. Yeah, so those are large enough models. So we want to keep benchmark accessible to people. So we try to make the minimal representative models to do it.
That's really great.
Yeah.
Yeah, thank you so much for sharing. I think it's a really good point to think about the inference cost, especially for these large language models, and how do we reduce the overhead from the system, or even think about how to reduce the carbon footprint when serving these different large language models on data center. Because of the time limit now, we have talked about system for machine learning. Maybe it's the right time to discuss a little bit more about machine learning for system in our next section. So the first question in this section is, there have been multiple efforts on automating the process of chip design using ML or RL by groups in industry and academia. For example, there is also a ArcGIS recently published by Harvard University. So people have also been thinking about how to decide the best architecture and maybe like scheduling mechanism using machine learning algorithms. And in the compiler space, there are also people trying to substitute the search problem with some reinforcement learning for better design space exploration. So what is your take in general on this whole line of ideas of automating the operation of building or designing of the systems using machine learning? And what's the major hurdle of applying them into like a broader area in the real system? Yeah, thank you.
Yeah, I can take this since I'm working on machine learning for systems.
Yeah.
So I think, first of all, it's very promising. That's why a lot of people working on this, right? A lot of groups, including industry. The very reason, or the fundamental reason, my view of the fundamental reason why this is promising is because, in traditional systems or the procedure of building systems, there are a lot of heuristics, human-baked heuristics, right? How we're going to design this. For example, you mentioned chip architecture design, whatever, right? There are going to be some algorithms which is based on human heuristics to design how we're going to do this. But that may or may not be the optimal way to do things, right? So I think deep learning, reinforcement learning, and some of the machine learning techniques are a very good way to jump out of the box and just to let the machine to learn the heuristics. At least from those experience people have, usually they can provide better solutions to that very specific environment and problem, right? On the other side, I also think there's also a trend, excuse me, there's also a trend of using neural network as a data structure inside computer systems. As I mentioned, so there are people using neural network to replace index, which used to be B tree, right? There are also like people talking about using neural network to replace hashing, hash tables and stuff like that. So these type of work also kind of interesting, and also people do see real world benefit of applying those neural network based data structures to replace traditional ones. But yeah, so I think in general, like finding better heuristics and using neural networks as efficient data structures are the reason why I feel like this is pretty promising, from a very high level.
Mm-hmm.
Yeah.
Great. Yeah, thank you for sharing your thoughts along this line. And I think definitely there are a lot of open spaces in terms of how to automate these solutions and, for example, replacing some of the most expensive data structures with neural networks. And there is another slightly tangent question. How effective do you think performance modeling with machine learning can be? For example, there are some concerns in the operating system community. If we replace a part of the decision heuristics with machine learning models, there could be scalability, generalizability, or efficiency concerns when using ML. So do you have any thoughts along this line?
I don't have a specific, I'm not an expert on operating systems, so I'm not familiar with heuristics they're afraid of replacing. I think there would be a general tendency to try to get rid of human written heuristics everywhere it's possible, not specifically in OS. And remember when I mentioned when I got interested in ML in 2008, right, that was actually trying to replace heuristics in compilers. Why? Because I work on compilers for years. I know how bad those heuristics are. I know how fragile they are. So I know that that's not a scalable solution moving forward either. Like someone wrote one heuristics to how to do unroll and this optimization, and then the person leave, the company, and good luck figuring out what the dependency. So we need a more systematic approach to that rather than manual heuristics. So if someone afraid replacing them, that's more like a conservative tendency of keep doing what we used to do for many years. I think we should try new techniques. Obviously, we need to objectively judge them. One criticism I've seen against ML for systems, in some pumps, people are overly excited and try to use it everywhere, and then make strong claims and that it's not validated afterwards. So we need to be careful and do proper research about it. But that's not the reason not to do it. Let's put it this way. Just as everywhere, you need to do proper research and properly validate it, right? I think in systems, checking this heuristic is a bit easier. I think it's more challenging in hardware. So if you start to try design chips using ML, that's a more open problem. I've heard mixed signals from Google, like some people were excited to use them to design new chips, but some people who design them actually criticize on the outcome, on quality of that. But that doesn't mean we shouldn't use it. It just means those techniques needs to be refined, and you check where they don't work and then improve the models. But I think those manual approaches like heuristics should gradually go away, right? Hopefully for better with a more systematic approach.
Yeah, exactly. Thank you so much for sharing your thoughts. I think the community should be open to adapting these new solutions, and also I think the ecosystems of how we collect data for these MLSys would also be more important, because as we talk about data-centric computing, collecting better data for these downstream MLSys tasks would be also crucial for enabling a better design our methodology improvement in this area. So thanks for sharing. Now moving on, I think we are having about 10 to 15 minutes left. So we would like to know a little bit more about your suggestions and advice for students or professionals working in the MLSys area. So maybe Tanvi, do you want to take over the question? Yeah.
So yeah, mainly we wanted to discuss what are the most important priorities for system researchers who are working in this domain, and if there is any like often overlooked sub area in MLSys, since more and more people are working on using this hammer and trying to find which nail is the best, but it doesn't work all. So just general advice that you would like to give to the student working in MLSys.
So, sorry, so the question is about what areas we think in MLSys is promising? Is that the question?
Yeah, what are the most important priorities for the students? Like what should they focus on? And what are the often overlooked sub areas that what we should not focus on, but people.
Yeah, I can go ahead. So I think the priority, I feel like you know, for at least for today's you know okay, so let me focus only on machine learning for systems. I'll leave system for machine learning to Gennady. But I think for machine learning for systems, all the work or the the recent future direction that I've seen require a pretty strong system background, because essentially you're trying to improve systems, again, so building better systems, whatever better means here. So the priority gonna be you need to be expert in systems, and then you need to, of course, familiar with deep learning, machine learning. But since people have really good infrastructure today, right? So they're very easy to use, thanks to a lot of the machine learning community, where they build this PyTorch, and also deep views and these easy to use compilers. Like that part is not super hard. But then in terms of the next question about what areas or sub areas people should work on, or you mentioned overlooked, I feel like it's really hard to tell until you actually see the true problem. That's why I think in the very beginning, both of us mentioned industry, right? So that's where you got the true problem. And I mean, there are motivation come out of blue, right? But usually the problem actually coming from the real world problems, right? So, and then if you have the motivation, have the problem, and then you have solid background, and then, sometimes it's, sometimes the solution of the ideas are already pretty much there. So you can keep moving forward, and then, the project is going to be pretty much easy to find. So what do you think, Gennady?
Yeah, I think I agree with you. I think I would reiterate again on me, like when I hire students myself, I usually want people with not like, it's quite demanding. So I want people had systems background, computer architecture, and some of the ML, right? Because that would help them to move faster. And that's quite demanding from an undergrad, especially, right? You could be weaker in one aspect, but you need to, like, I don't typically hire people with just ML background. Let's put it this way, because I feel like it's easier to teach a systems person some of the ML than the other way around, right? So it's easier to move from C++ or C to Python than the other way around. Let's put it also this way, right? So in terms of areas, since we're talking about system for machine learning, there are some areas that are clearly of importance right now, and there are areas that would gradually emerge, and you never know, right? And that, as Cheng said, is you need to look up for them. Again, you can come up with ideas just by thinking, but I usually come up with problems first and then solutions afterwards. So I don't want to be like sometimes people in theory do, having a hammer and looking for a nail around. Like I would rather find the right problem from the beginning. And why working with industries helps, because they had all these problems. They just don't have time to work on it. They need to deliver quickly. They sometimes don't see what would be the problem a year, 2 years from now. And we had a larger focus, like we can take on more risky projects that might be not justified in industry right now because of their budgets. So this is our advantage over industry. So we take on more risky projects. So in terms of, there are areas that already clearly emerge right now. So one, obviously, that a lot of my students are working as machine learning compilers. This is not just mine, like a lot of groups right now work on that. As with any hot topic, the problem is it's crowded, right? So over time, you need more and more expertise, right? But there are a lot of other very interesting areas. Like I'm very interested recently in intersection of security and machine learning. It's a very promising area, in my opinion. I don't think it's as crowded, right? There are people working on it, but more in the ML side. I try to look at more from a system side. So a lot of very interesting problems that you need to solve there. So a lot of people start to look at how all these, powerful language models will apply to different things, like say bug detection or code generation. That's very interesting, right? Again, it's a hot topic right now. I think it's very interesting on to what extent humans, programmer labor can be assisted properly. I don't believe at this point the technology can replace a programmer, but I think it can be a good assistant. So where are the limits of that, how we actually adopt it, and that's a very interesting open problem. So sometimes it also goes into HCI area, right, which I'm not an expert, but we did some papers in this space because it's important to address that thing as well. So there are a lot of very interesting problems. I say if you're a new student just joining the area, you shouldn't think about what my PhD thesis would be immediately. What you should be looking at as the right problem to solve. And the right problem, why is it so tricky, is that you need to find something big enough that has an interesting contribution in the vision, but something that is actually tractable in 3, 4, 5 years, right? So this is why it's a challenge. It's very easy to find a simple problem, or it's very hard. It's also easy to find something very complicated that is hard to solve. Something in between, that's what's difficult, right? So I wouldn't focus going especially into PhD right now on what to work on immediately, rather than what the skills I should possess that I will be able to tackle an interesting problem. And here, diversity of skills is very important. I think not just being, a monkey that can only do one trick, but rather being prepared to do a lot of interesting things.
Yeah, that's a really interesting point. So since you mentioned that it's easy to go from systems to ML, like you would prefer that, and there has been a lot of hype around this area, and many people are working on it. What do you think about future? Do you think it will remain equally important in, say, next 10 years? Will we actually need so many MLSys specialized people, or will it die down that we would have exhausted the applications? What do you think about the future of MLSys?
Well, I don't have a crystal ball to speak about 10 years. Even 5 years prediction is hard enough. Like just think about it for a second. Take a clock 5 years from now, transformers were just invented. Who would know the ultimate impact of them, right? Immediately, right? And that it would scale and all those things. So a lot of things can come up. But I personally feel that ML as an area, not necessarily even transformer, but the fact that we were able to do a breakthrough of something, we solve certain complicated cognitive tasks that we before believed would take 20, 30 years to solve, right? If you look at the roadmap before, say, computer vision, before AlexNet, people thought it's going to take us 20 years to get to the human quality, on object recognition of this task. And we just did it in 3 years, right? That happened because there was a big breakthrough. You don't never know, but I feel like the whole ML area will stay with us. Since industry jump on it, it means it's going to be deployed. So systems aspect of it is not going to go away. It's ML could exist without system for a long time because it was an academic area on its own. You don't care if you just want to train the model to solve an idea. You don't need it to run very efficiently. You just need to show that it works, right? A lot of NeurIPS papers to this day, they only show the accuracy curve, and they don't even bother to show how long it takes. It's less and less so, but for a long time, they just show curve without runtime, right? But now that all of that has huge cost and all the associated problems. So I think because industry is on it, ML system as an area is definitely something worth investment. If I can make a prediction for the next, there is inertia. So I think unless something ridiculous and big happens that it invalidate everything, I think for the next 5 years, it's a very good investment of your time, I would say. Yeah. So I don't think it's good. It's only started. I think industry just started to adopt things. Of course, Google and Meta adopted things for a while, but now we're talking about, Bloomberg, JP Morgan, hedge funds, they started to adopt it, right? So they're usually slow, and if something starts to adopt by them, that means it's already a mainstream thing, and it's going to be many years of adoption moving forward.
Yeah.
Yeah. So I saw a question or rather comments on the chat, where I think the comments about industry might not actively communicate their problems. Yeah, totally. I think that's why we need to build this really good collaboration relationship with them. We listen to them, and they if they have hard problem, they will find us. So so back to the question of like 10 years. I'm more positive, I guess. I feel like MLSys is gonna stay. So not mention, for example, compiler already, a pretty basic infrastructure. So all those deep learning systems gonna stay, right? People need like companies or the entire ecosystem need people to do those, right? People they need the expert who deeply understand all of this, because machine learning and deep learning, they change a lot. Sometimes companies need those experts to optimize for certain things, right? On the other side, as Gennady mentioned, there are people. I know there are companies start to apply machine learning for systems in their production systems. For example, I think Redshift, which is a distributed database of Amazon, they actually apply some of the deep learning stuff in it. So, in general, I do think in the future, in the next 10 years, industry going to need more people who know both systems very well, and also deep learning and machine learning. So I'm more positive, I guess. Yeah.
Okay, great. That's all the time we have.
Yeah, if you don't mind, there's a comment on this message in the chat. I think it's important to say that we as researchers, in my opinion, should take a more proactive stance here. You can't expect that Meta or Google come to you and bring problems to you. You have to come to them and find what their problems is, right? That's not going to be the other way around in most cases. Yes, we build different channels to communicate with them. They talk about particular problems, but they would talk about the problems that already identify themselves. They're probably already working on solutions as well and might need some help. But if you want to find something they didn't figure out, you need to come meet them, give talks there, do internships there. That's the way you would learn what the problems are there, right? So I think don't expect that it will be communicated with you by someone. You need to be proactive to do it.
Exactly. That's a really good point. And that's all the time we have for today. A big thank you to our guests, Professor Gennady and Professor Cheng. It's a huge honor to have you in our podcast, and for having your insightful responses to our questions. And we hope you all found this discussion as enlightening as we did. And please stay tuned for more discussions related to computer systems in the future, hosted in our channel. And until then, this is the end. And thank you so much again for joining us.
Yeah, thank you for the invitation, Eugene and Tanvi. Thank you, guys.
Thank you. Yeah, thank you, Gennady.
Thank you for hosting this.
Yeah, thank you. Bye-bye.
Have a good day.
Bye.
Bye.